think this is a rather good transition to look back what happened some time after the events we had dedicated to 50 years of Anderson localization 4 years ago. And here here I used two figures from, in fact, 4 years ago there were two programs in parallel. One about turbulence, another was about Anderson localization in disordered system. So here you see one figure from the report of turbulence program, and this is figure from the report of Anderson localization, more familiar for people here. And here you have some turbulent flow, and this is our image of a turbulent wave. Now, I like maybe to start with the first sentence of his letters written in poetic style of Vladimir Zakharov. Though mechanism still only partially understood, wind transfers energy and momentum to surface water waves. And I will try to trace maybe parallels between Kolmogorov turbulence, Anderson localization, and KAM integrability following this archive paper. Now, what we can tell about turbulence, Kolmogorov turbulence in this concept? It's Kolmogorov 41 paper and also related paper of Obukhov, where he proposed some dimensionless arguments with the idea that there is a flow of energy from large scales, maybe large vortices, to small vortices in the turbulent flow, and this energy is some kind of current. And then on small scales you absorb this current due to dissipation. And he wrote the distribution of energy density in K space, that if you have this energy flow J, then this density is proportional to J in power 2 over 3, and wave vector K minus in power minus 5 over 3. So I will not give derivation, well-known result in turbulent community. And for many years it was remained like not rigorously derived. And then there was paper of Zakharov and Filonenko in 67 done in Novosibirsk about surface waves on deep water, and they used random phase conjecture. They considered nonlinear interactions of waves, and on the basis of this random phase approximation they essentially obtained also power law distribution of energy density. For this flow, when you assume that there is flow energy from big scales to small scales, then they obtain some kinetic equation, and there is a book on that written by Zakharov, Lvov, Falkovich. And well, since I was in Novosibirsk, I heard nice lectures of Lvov, maybe 30 something years ago about all this stuff, popular in Novosibirsk. But somehow it was always in the frame of random phase approximation. We assume ergodicity, and then we write our kinetic equation, and we see that there are such kind of solutions there. But well, now, and maybe some ships were, Soviet ships were, liners were in the ocean trying to measure this turbulence and find this power laws. But maybe now we are on a small scale. We have some small basins, we shake them, and with this laser we can measure the waves. So we come to finite systems. And the question is what really happens in finite system, and we should somehow justify this random phase conjecture, which not always will be true. And somehow you may say that in finite systems the spectrum of linear waves is discrete, and then maybe there are resonances and there are discussions in this turbulent community how this resonance between linear waves can influence, because usually this you consider 3-wave or 4-wave interaction due to nonlinearity in the medium. And then if your spectrum of linear waves is discrete, then maybe nonlinearity will be weak, so you will not jump between resonances. There are works of Kartashova and Nazarenko on that, and in fact there was talk of Nazarenko in 2008 about some numerical simulations of nonlinear Schrödinger equation in a finite system. But even if a spectrum is discrete, then you get suspicion that maybe not always this flow will go from large scale to small scales, and there should be some chaos border below which this flow will not appear, and this, like a small wind will definitely not produce turbulence in the system. So flow will not go from large scales to small scales. But then from solid state system, we know that even spectrum can be pure point spectrum everywhere dense, but we will have Anderson localization. So the current will not flow from one side of the sample to another one. And here in this language, K-space is like a coordinate space. For turbulence, we work in K-space, and in solid-state system, it's real space. So we know that if Anderson localization happens, and even if our spectrum is everywhere dense, still we will have no flow. So this gives idea that you may have some interplay between all of this system, and maybe this Kolmogorov flow will have some analogies with Anderson localization. So Anderson localization may happen, and then turbulence Kolmogorov turbulence will not exist. Of course, turbulence is always nonlinear system. So in fact, we arrive to questions about some kind of KAM theorem. If nonlinearity is small, and in this weak wave turbulence, so nonlinearity in this works of Zakharov, it's usually assumed to be weak, relatively weak, and there's no border for how weak it should be. While in KAM theory, we know that there is border for appearance of chaos, and also this goes to Fermi-Pasta-Ulam about questions when in dynamical system with many degrees of freedom you have appearance of ergodicity, and when statistical mechanics sets in. So this in this many-body system, this weak nonlinearity. In fact, this is the next line of Anderson localization program taken from the talk of Anderson, and it's very nice to be able to see the talk on the web at Newton Institute. And the end of the talk, in fact, there was only one question about perspectives, how he sees futures of Anderson localization in general. And his answer was that we should look at this in new type of physical systems or to study effects of interactions. Well, on point A, I think there was a good progress in last years. In fact, experiments with cold atoms in kicked optical lattice done by Jean-Claude Garot group at Lille. They observed Anderson transition in 3 dimensions and measured exponents which are close to those we expect from analytical theory and numerical simulations. So I will not speak about point A. Point B, effects of interaction. Of course, real many-body quantum system are too difficult, even 2 particles are under continuous discussion. So let's make a nonlinear perturbation of Anderson spectrum. It's interesting even from mathematical viewpoint because it's everywhere dense spectrum, but states are localized. So let's add nonlinear perturbation and see what will happen. Somehow we were going not directly in that line, but it was related. Our early work with Arkady Pekovsky started at Novosibirsk. Because in Novosibirsk there was quantum version of Chirikov standard map, also known as kicked rotator. So the idea was to take, so this is a particle on a ring, quantum particle, some fixed mass, and you have kicks, and this was discussed here maybe. And then these kicks follow periodic in time, and in classical, for a classical particle, you have this Chirikov standard map, and if a nonlinear parameter, dimensionless nonlinear parameter is bigger than 1, then you have global diffusion in the system. So in a sense, here you have just this example. You pump energy on small scales because you kick with cosine x, which is 2 pi, and then energy goes from small k vectors to large in classical system, but due to phenomena analogous to Anderson localization, even if system is purely deterministic, this classical diffusion is localized, and this is one of the examples. Of course, system is linear if beta is 0, but there is no flow from large scales to small scales. Now let's add a nonlinearity, this nonlinear Schrödinger equation, and keep the kicks. If beta is pretty large, then the size of soliton is pretty small. We can neglect that you are on a finite ring of size 2 pi. Then soliton is kicked, it moves. In fact, if it's in chaotic component, it's moved chaotically. This small lines is the size of soliton, and it's one soliton trajectory at relatively large nonlinearity beta 5. If you take its integrable component, it moves in an integrable way. But kicks leads to evaporation of soliton, and on long times it disappears. So there is interesting question: what will happen when soliton is destroyed? And those times we observed that classical diffusion is not reproduced in system if you have nonlinearity. Well, of course, without kicks, it's integrable system, as was shown by Zakharov and Shabat. But kicks in classical system produce chaos, so you may ask how all this nonlinearity, dynamical localization, analogous to Anderson localization, and all these things will play in the presence of nonlinearity. There was this result showing that there is some growth, but those times not was quite clear how it goes, and maybe it's still the case now. So to improve the simulations, the idea was, well, to run. Of course, nonlinear Schrödinger equation is the real nonlinear wave interaction, four-wave interaction, what we want like to have in this kind of systems like a weak turbulence. And it's experimentally realizable now with Bose condensate or nonlinear medium, so it's a realistic case. But for numerics, maybe a bit heavy. So the idea was to take, let's in the momentum space, let's add some nonlinear shift proportional to beta to the phases in the basis of linear eigenmodes, psi n square, and this is much faster. So there was situation what was shown numerically. These are old data with kicked nonlinear Schrödinger. Now this kicked nonlinear rotator was going for a longer time, and you see some subdiffusive spreading. So sigma is the square second momentum of probability distribution in the system. Probability is conserved, but this happens if nonlinearity is relatively moderate, let's say order of 1. If you take small values like 1/20 or 30, then you see that sigma remains bounded for available numerical times, and now there are more extended numerical simulations, also maybe the most advanced by Flach group. And the slope here is that the momentum grows like 2 in power 2/5, approximately 0.4.
So are you showing here this is the right-hand picture, is a localization picture more or less? Or what?
Yeah, this is like KAM regime. So I say weak nonlinearity doesn't destroy localization.
Yes, yes.
While if it's bigger than some critical value, I see it's not real diffusion, it's
actually subdiffusive.
Subdiffusive with a power with the exponent alpha 0.4 approximately. That's the straight line here, and I had at those times some arguments, and I will maybe flash them.
So
in fact,
this is
there are two models here.
yes.
The full curve is this nonlinear kicked rotator with nonlinear phase shifts, full curve, and points are from kicked nonlinear Schrödinger equation. And I will show more advanced numerical data for kicked.
Those are different models, right?
These are different models, but in fact, I will show that the exponents are approximately the same.
But the rate,
So there looks to be in the same universality class.
the rate plotted is simply
The right if nonlinearity is weak.
smaller k.
No, beta non-linearity is small, 1/30. So it's like in the spirit of KAM theorem. So if non-linearity is weak, then we will not have energy transfer from.
How are you sure that if you run the right flow,
Yeah.
you can start with
Maybe it's appetizer, my talk before the lunch. So there will be no heavy theorems, no rigorous statement. It's physical talk I show. But my argument is the following. Yeah, it's a good point, Shmuel, that here you start, if beta is 0, you are in linear system, the localization length is maybe here, and for these conditions, you can measure it numerically. It's about 2, 3, order of 1. And I go to time scales 10 to the 7 and even 10 to the 9. So how you combine from numbers which are all order of 1, scales 10 to the 9. So there should be some physics behind. I'm not claiming that I explain it, in fact, but I will give some ideas. So what is, and the related model is nonlinear Schrödinger equation with disorder and nonlinearity. So I put this discrete version of Anderson model with nonlinear phase shift. That's for a short Dan's model. So it's clear that we know practically everything now after 50 years, let's be honest, from physical viewpoint, we know everything about Anderson localization, at least in first approximation of physicists. So we know the eigenstates, their properties. So if we neglect this term, everything is localized. Let's rewrite this equation in the eigenmodes of linear problem. And then all hoppings will happen. This is simply rotational phases of this linear eigenmodes. And hoppings goes only due to nonlinearity on this three-wave mixing, but eigenmodes are localized. So here it's difference from turbulence that modes are localized in coordinate space. But I will show that in a sense, even in the space for nonlinear Schrödinger equation in space, the situation will be similar. So we have C cube terms here, which gives hopping. So you can write some kind of Fermi-Golden rule, which will give you the transition rate C to the 6. And since the norm is conserved, C is inversely proportional to the width of the wave packet square root of that. So you get that the rate of jump is inversely proportional to delta n in power cube. So you jump on the length of order of localization length. So you write your diffusion that delta r square over time, delta r square over time should go like this diffusion rate, gamma. This decreases like delta n in power cube, or for arbitrary dimension. If you insert arbitrary dimension, you will get a subdiffusive growth with exponent alpha, which is 2 over 3d plus 2. For d equal 1, you will get 0.4 approximately. And numerics is maybe it gives a bit less, 1/3 maybe, or it depends. And for 2D, it's also 0.25, and in 2D I will not show data, but numerics goes approximately like that. So the original idea was that why it goes like that nonlinear shifts induced due to nonlinearity may be comparable with the resolution of uncertainty relation between frequency and time. So on a time t, if you have delta n modes excited, you resolve the frequency is 1 over delta n, and then you see that the dependence on delta n here is of the same power. So if your beta is bigger than 1, then nonlinear shifts are bigger than your resolution. And then chaos can persist for very large times, but maybe there are now data with different types of nonlinearity where with higher powers of size.
But you want to tell that it is always the diffusion, so
Subdiffusion.
I mean subdiffusion, but not localization, never localization.
If beta is bigger than some critical value, I showed you. You already asked me. I showed examples that beta, if it's small, then we are like KAM regime.
So there is a transition.
Yeah, there is. But it can be maybe not a real transition. Maybe they will become layers very tiny, and I will go to that. So
But it
this
doesn't depend on the sign. On the sign would be
no sign doesn't.
because of the discrete.
Yes.
Yeah, sign doesn't matter here. It's so there are some numerical data, maybe more advanced, obtained in 2008 with Arkady Pekovsky for different. For this is nonlinear Anderson model done there with some disorder strengths 2 and 4. So your localization length here is about a few units of 1, maybe 5, 4, maybe something like that. And you see that this average over some number of realization over disorder. So the second mode grows with the exponent approximately 0.31, 0.34. Well, maybe the accuracy, statistical accuracy is not so high, and the tails are of course exponential because here nonlinearity is negligible, but there is a chapeau or plateau which size grows with time, and this goes in this subdiffusive way.
So there is a theory exponent and
Theory is
does not
this estimate which I showed was given 0.4, and here the slope is shown 0.4. But if you fit this numerical data, you will get the slopes for 0.34, 0.31.
so it means that this theory was not sort of fully controlled.
Yeah, I think it's not so
And
really.
it is consistent with what Flach is talking about. Or-
Flach has his own arguments. I'm not sure I understand
I know-
them
I know
completely.
Flach
He gives
arguments.
1/3. He gives 1/3. But well, the point is that you can start to change the power of nonlinearity, and then there is a dependence on this power. And I don't think that theory
We're
really.
talking about 0.3 as far as I understand.
Yeah, 0.3. Yeah, but well, I will show other numerics which is more close to 0.4. It's
To argument for other nonlinearities. What is the result there? Instead of 2, if you have the nonlinearity with some power sigma, instead of 3.
well, the point is that when you should increase nonlinearity, and then you spread more slowly, so numerics becomes not so.
It's impossible to do it numerically.
Well, you do, but you see some exponents. But even here, I would not bet.
No, but what
that
will your argument?
yeah, I will come to my point later. So, some for kicked rotator, I was discussed. You can go 10 to the 9, and here the fit gives you. Well, if you want 0.39, well, this probably are the most long runs available now because it's kick, so it's numerically efficient. And you see here how you start, and this plateau start to spread with time, things like that. So, but this is the global picture. The size of plateau grows, the tails are exponential. Then you may, if you take smaller system, you can say, well, large system difficult to handle this equipartition or quasi-ergodicity is long time to take. So maybe you should test some thermodynamic hypothesis in simple lattices. So this is possible to do, and that's another work with Arkady and his students. So you may say this again the same Danse model. You diagonalize it, you find eigenmodes, and you start from one linear eigenmode, and then you evolve in time, and you compute the distribution over these eigenmodes, and you compute the entropy averaged over time, order of 10 to the 6, 10 to the 7, when you reach the equipartition for small lattices like 16 or 32 here. And in fact, it's funny, if you plug in thermic distribution, Gibbs, you say Gibbs is valid, there is some temperature, then I should have these energies divided by temperature. And temperature, you say, appears because I have nonlinearity, so there is some dynamical thermalization in the system. And over this linear modes, I will have thermic distribution. You plug a Gibbs here, and you trace entropy versus energy with this ansatz, thermic Gibbs ansatz. And this is the blue curve, and from numerics, indeed, you obtain points which more or less follow the curve, some which deviates. You have deviation at the ends of the spectrum, and there are breezes, Aubry-Mackay breezes, so definitely we understand that. But, well, this is for bit 1. If I would take bit 2, then it would be even better. So there is some dynamical thermalization behind. But, well, the problem is complex, and not everything is understood. There are various groups theoretically working on that, and there are experiments, and probably at the moment, of course, there are interests to experiments to study effects of nonlinearity. I maybe flash some of them. There are experiments of Sergei Technion, because he can create nonlinear media, and propagation along that is like time evolution, and Finkelstein spoke a bit about this experiment, so he sees that nonlinearity may affect localization properties. There is experiment of Silberberg and Weizmann, where he creates nonlinear photonic lattices, so nonlinear medium where nonlinearity enters in a classical way, and the nonlinearity may affect, in this case, also localization. There are also kicked Bose condensate group in Florence at Lens, maybe, but they have not real disorder. They took Aubry-André model, quasi-incommensurate potential in the localized phase. They added this nonlinearity due to Beck, and they see some subdiffusive spreading, numerical. They measure some alphas, which are this experimental fluctuations, maybe 0.2, 0.4, but something like that. Even if I would say that maybe experiments can hardly compete with numerics, even if they have plenty of atoms in this Bose condensates. So what is the current status? Well, numerically you see exponents 0.3, 0.4. Well, there's some variations, and the point is not, I think, here to bet on the exponent, but to understand what is really going on. And I think there was really good work done by Pekovsky and Fishman. What they did, they took this dense model of beta equal fixed, suppose 1, and then you start to increase the sizes. You go from 10, 20, 40, and so on, and you throw random trajectories, and you measure Lyapunov exponent, and by this Monte Carlo procedure, you determine the fraction of trajectories which are non-chaotic, which have approximately Lyapunov equals 0, and since Lyapunov is rather efficient computation, so you can distinguish by that, of course not rigorously mathematically, but you can see those Lyapunovs which are well stabilized, they are positive, you increase your time of computation by factor 10, you see that they are stable, while others decrease by factor of 10, more or less. So you distinguish them, and you can, in this way, determine the measure of chaos. And in fact, they showed that the measure of chaos, when you increase the system size at fixed beta and normal psi square normalized to 1, the size of chaos goes to 0 with the increase of system size. So this means that system is not fully chaotic at large sizes when it spreads, but it follows some chaotic layers which can become maybe tiny or whatever, and that's probably how it goes. So it's not ergodic on large scales, but maybe this chaotic layers goes to infinity, and the spreading will continue to infinity. And this is the question which brings us to Arnold diffusion. And here I would like to, it was nice story told by Kostya Hanin a couple of days ago, that well, last year's Arnold and seminar in Moscow, mathematical seminar in Moscow, when someone was speaking about Arnold diffusion, he was starting to say, why you call this Arnold diffusion? This is not Arnold diffusion. And Sinai stopped the quarrel, saying that let's speak to continue. And the story is that, of course, Arnold showed that you have this chaotic layers everywhere dense, and then you may have through them unbounded diffusion, but physical studies, in fact, Chirikov coined the term Arnold diffusion, his works, and he studied it a lot, and there is some I think, essentially unknown paper, even if it was published. It started in the first steps were published in the book dedicated to 60s of Mozart, and some, I think, 2 authors of this volume, rare volume, only 2 volumes in libraries of Germany are available. So 2 contributors are here, I think, in the audience. So what is Arnold diffusion? You say there are these tiny chaotic layers, but what is the size of the layers when you decrease the nonlinearity? And if you have 3 degrees of freedom conservative system, then you may show that it's related to the width. The diffusion rate is proportional to square of a chaotic layer, square width of chaotic layer. And it's inversely proportional to, it's proportional to minus lambda, it drops exponentially, and lambda is 1 over square root of k, some k is nonlinear parameter for the Chirikov standard map, suppose. We know quite well what is the width of chaotic layer when k is very small. So we go to small nonlinearity. But then this was the work, extension, maybe 7 years of work, Chirikov Vyacheslav, the last one published in JET in 97, that in fact they found in a very big range that the width drops in a polynomial way. And this implies that Arnold diffusion drops for quite a big range, huge range, I would say, of parameters like k in power some nu with nu approximately 6.6. I will show the data. K is nonlinear perturbation. So like perturbation of KAM.
Like beta.
Like a beta, yeah. And maybe let me show the results. They had a very precise numerical method because the layers, chaotic layers are very tiny, so you should start directly inside the chaotic layer. And they had this method, numerical method, and they studied, well, essentially coupled standard maps. Maybe the Hamiltonian is written here. And with up to 16 particles or 15 particles. And that's the data, that the logarithm of the width decrease with logarithm of k, which is essentially 1 over square root of perturbation, nonlinear perturbation, some power laws, and there is a sharp drop, but this is the story. And here you see that the diffusion is on the level 10 minus 50. That's maybe the best for Arnold diffusion. And the idea is that when we spread along this, but they stopped at 15 degrees of freedom, while when we put this under discrete Anderson model with nonlinearity, we have spreading over more and more levels, the number of degrees of freedom growing, and how these layers behave remains essentially not known. We had some. You may take, and the point is that in Dancet, the linear frequencies, they are fixed. They are constant because you start with quadratic Hamiltonian. But maybe more generic to satisfy Nekharoshev conditions. And in fact, Weiminck, I think, was she was one of the first mathematics who was speaking about this problem of nonlinearity Anderson localization from the viewpoint of Nekharoshev estimates and Anderson Arnold diffusion. So you may take more generic Hamiltonian, which is nonlinear. H0 is nonlinear, then coupled modes in nonlinear way, and say that it's maybe more generic because frequency depends on actions, not like in linear oscillator. And that's what we have. The spreading of this lattice, we also see some subdiffusive spreading. Maybe here there are some weak signs of maybe saturation after time or decrease of exponents, better to say, that may correlate with this tendency that at some stage it can decrease, but well, in this language we are somewhere here only. So you should go, I don't know, 10 to 40 in time dimensionless time units to reach this decrease. So this is the situation, and well, what is in fact for turbulence? This is a similar problem that will it spread or not, and well, maybe due to lack of time, I return back to this kicked nonlinear Schrödinger equation. If kicks are small or nonlinearity is small, sigma doesn't grow up to large times, you have exponentially localized profile, and so essentially everything like it was discussed, analogy between K-space and the coordinate space Fishman-Grenville-Prange, that this is localized. We don't have flow from big scales to small scales, so Kolmogorov turbulence doesn't exist in this nonlinear system. If we increase nonlinearity, then we are getting this subdiffusive spreading, and the exponent here is this is traced dashed line is again 0.4 for this kick nonlinear Schrödinger equation, which are for turbulent problems is much more natural, but that's what we observe. So the exponent is approximately the same, so it seems that local interaction of localized modes is not so crucial. Even if we have modes in space, this will be the case, and we can say maybe if you similar situation will happen if you apply monochromatic microwave perturbation to a particle in chaotic billiard. Like here you have localization in the number of photons. Some work with Thomas Prosen done some years ago. This is linear system. You may say, what will happen if inside this billiard you have Bose condensate? So it will be Kolmogorov turbulence in Sinai billiard. Will we excite high modes? Will be the energy ergodicity and energy flow from large scales to small scales? At least the preliminary data in some model system shows that it's strongly suppressed in that case, and the ergodicity doesn't and chaos doesn't spread from large scales to small scales. So this is I come into my conclusions. So I think there is interesting parallels between nonlinear perturbation of Anderson localization, pure point spectrum, and first nonlinear weak perturbation. What will happen if there is a delocalization transition due to nonlinearity, and if at some moderate nonlinearity we have unlimited spreading. Up to now, all numerical data indicate that the spreading continues to all available numerical times order of 10 to the 9. But it's definitely not ergodic, because according to result of Bukowski-Fishman, the measure of chaos at large sizes goes to 0. So we follow some Arnold chaotic layers with probably fast Arnold diffusion according to Chirikov-Vyacheslav. Thank you for your attention.
Questions? I have the following question. So we have actually we've heard two presentations, one by Sasha Finkelstein, the other yours, and it is essentially about the same problem. I have an impression.
But different sides of that problem, because Sasha he was interested in the case how diffusion is affected by nonlinearity, while I am in the situation when diffusion is stopped by Anderson localization.
Okay, so you are from the other side.
I'm from the other side.
You go from the other side. So my question is the following. So basically, Sasha introduced for the first time, in my opinion, an important notion of collision integral in the description of this problem. And this collision integral is because of nonlinearity. And one of the business of this collision integral is to produce a dephasing that kills, that may kill localization. What you say as a mechanism to escape localization is Arnold diffusion. My question essentially is, so that there are two possible scenarios. Is there anything common in them? So is these two completely different in your opinion, or it is related?
I think there is no links with the results of Finkelstein, because he is in the diffusive part, and he asks how diffusive modes are affected by nonlinear. While here, this collision integral, if you call it's written in localized eigenmodes of Anderson problem. So you see, here jump goes not more. If one is excited at M0, you cannot jump more on localization length. And you jump only due to nonlinearity. Otherwise, if nonlinearity is 0, you stay localized. So you should understand how this nonlinearity affects these jumps. Indeed, there are many interesting questions, because this overlap integral between localized nodes is formally you can write it, but it's correlated, which is non-trivial even for Anderson problem. Maybe Dorokhov, Garkov had some insights on that many years ago, but it was not so much studied. It appears also in two-particle problem where delocalization happens due to interactions. The same integrals and same things appears, but it's not the same four-wave interactions like in Finkelstein, because they are over-localized modes. So that's only.
We have had our appetizer, and I presume that we are very hungry now.
Let me just.
Just now, okay.
So I have a few comments, but the main comment is, I think, since we are in the Mathematical Institute, I think it's a problem of the type of problem that probably should be resolved by rigorous mathematics in the end, because it's very difficult to resolve it in some way by numerics. Now, concerning the first comment, we looked at the nonlinear term, and for some cases where it looks as if it's noise, so it looks as if it's noise because of chaos. Now, but the tricky part is
It's time dependent noise, right?
it's time-dependent noise.
That's
yes.
important to say.
It's time-dependent noise. Well, in this field called time-dependent, the noise is time-dependent. Then, however, there were realizations of the random potential of a diffusion, where the subdiffusion was not observed, and then the nonlinear term did not look as noise, and as time-dependent noise. And specifically, we looked at the power spectrum and the width of the power spectrum compared to the length that it was done. Second, then the part that Dima mentioned, the work with Pikovsky, basically what it looks as if there are realizations where there is spreading and there are realizations where there is no spreading. As time goes, the number of realizations, the weight of the realizations where there is spreading will basically, it decreases. Now, and then, then there are also calculations by Serge Aubry that looks on the number of realizations where the motion is quasi-periodic. And again, it comes to a conclusion that it looks as their weight increases. Now, and then, what no one succeeded is to have values of parameters, and that would be nice if someone succeeded. Well, in the beginning you see subdiffusion, and then seeing that it stops. So no one succeeded in finding that. And in addition, these were conjectures that were based on the work of Wenning-Wang, basically suggest that the spreading crosses over from this subdiffusion to logarithmic or weaker. So, and this is something that in some way, now the problem also in the work with Pikovsky, since it's a Lyapunov exponent, we don't see the effect of Arnold diffusion, because it's a zero Lyapunov exponent quantity. So therefore, the situation, I think, is generally unclear, and it's the type, and now there is I think, a danger with numerical calculations, because when we do numerical calculations in the chaotic component of a system, there is theoretical support.
Yes, well, I don't agree with this statement. I
Okay.
think that's a simpler
Can come close, because organizer becoming increasingly agitated.
So that, so I would say it is more. I would say it requires some justification. We have shadowing, and this is the justification for calculating average. Here, I don't know, but it may be correct. But I don't say it's not correct. It has to be checked. So, but this is something that I really believe that pure mathematics can really help you.
That's
Okay, yeah, I guess Dima wants to comment on something.